we have defined prevarieties to be ring spaces which have a cover by affine varieties. And we have seen that affine varieties and the open subset of them again give us prevarieties. But now we would like to construct some things which don't come just as open subsets of affine varieties. And for this, we need basic new construction because we can get new prevarieties by patching them together from patches which are affine varieties, or more generally, from patches which are prevarieties. And this is the following construction. And we start a bit modest and just take two prevarieties, x1 and x2, which could, for example, be given by affine varieties. And we want to glue them along some overlaps. And so to make this precise, we say that u12 in x1 and u21 in x2 are open subsets, and to glue them, we give an isomorphism from one to the other. And then our goal here is to define a prevariety x, which intuitively should be given by gluing this patch and this patch together along F, like this. And we construct this prevariety x in stages. So we work ourselves from the ground up. We first define it as a set, then we give the set a topology, and then we define the structure of a ring space. Okay. So to get it as a set, we can start with this disjoint union of these two sets, and then mod out by an equivalence relation, which identifies any point A here with this image point f of A on the other side. And for symmetry, we need to do it also the other way around. This is one thing. And then to be also reflexive, we want that our relation also satisfies x is similar to x for any x in here. You can check this defines an equivalence relation, and we define x to be the quotient, so the set of equivalence classes. And then, well, this just exactly identifies these 2 points as we want. And we get 2 injective maps from x1 to x and x2 to x, which map any point to its equivalence class. We can first go from x1 to this disjoint union and then go to the projection to the quotient by the equivalence relation. Then can immediately check that these are injective maps. 2 points here map to the same thing if and only if they're actually equal. And so we can see x1 and x2 as subsets of this glued space X. Now, as the second stage, we want to get the topological space, and we do something very similar. Well, we have, of course, a topology on the disjoint union of 2 topological spaces, just by standard construction. And then we have this set theoretic map to X as constructed above. And the idea is we get a topology here by putting the coarsest topology, making this map here continuous. This is sometimes also called the quotient topology under this equivalence relation. To make it explicit, you can say that U inside X is open if and only if the pre-image in here is open. So in other words, if the pre-image in X1 is open and the pre-image in X2 is open. So this gives us a topological space. And then what you can check is that I1 and I2 are homeomorphisms onto their images. So I would say this is a short exercise, but well, how you would prove this is I1, we have already seen, is a bijection onto its image. It is continuous by the definition of this kind of coarsest topology. So you only need to show it's open. So you have an open set here. Why is its image in X open? And here, I mean, the one thing that you need to check is, let's say you had an open set here. You take the image. Why is this thing open? Well, you need to check that the pre-image in X1 is open. This is fine. It's the set that we started with. And the pre-image here is also open. This will be some part here. So you need to convince yourself, why is this thing open? That's a kind of short argument. using the property of f. Okay, now I have basically done the whole exercise. Okay, and so these are homeomorphisms onto the images, so we can, as topological spaces now, see x1 and x2 as open subsets of x. And then the final stage is we want to get it as ring spaces. So we define the structure sheaf OX by saying that sections on U are just the functions from U to the base field K, which satisfy that if you pull back under I1 and I2, this function, then you get a regular function on the corresponding pre-images. So, I mean, it's very similar in spirit to this, that you say it's open if and only if the pre-image is open. And kind of the slogan is the function on U is regular if its restriction to x intersect x1 intersected U and x2 intersected U is. And then another exercise, which I won't do now, is that this satisfies the sheaf axioms. And it will follow just from the sheaf axioms of O of x1 and O of x2. And so indeed, we get a sheaf of K algebras on X, and this makes it into a ring space. And again, we have the final identification that these open sets x1 and x2 and x, you can see that the sheaf of functions on x, which we defined here, if you restrict it to xi, then you get the sheaf of functions on xi. And so we can see them also as open subset, as ring spaces inside X. And then once you know that, the fact that x1 and x2 are covered as ring spaces by affine varieties, then take the union of these covers, and this gives a cover of all of X. And so indeed, we have constructed a ring space to cover by affine varieties, so X is a pre-variety. We have gotten our hands on a new kind of pre-variety. And as an application, we now want to see two ways of gluing the affine line A1 to itself. So in our construction, x1 and x2 will be the affine line, and the open overlaps in both cases will be the affine line minus the origin. And so the remaining freedom that we have is how do we identify A1 minus the origin in one of the sides and A1 minus the origin in the other side. There will be kind of two natural choices. The first one to look at is the function f of x equals 1 over x. Certainly, if you have a non-zero number x, then 1 over x is still a non-zero number. And this is a well-defined map, and the inverse is just given by f itself, because 1 over x is equal to x. So this gives us, this is all the data that we need, two spaces and a map between the designated overlaps. And so what do we get? And at least as a set, we can describe easily what we get, because x is covered by x1 and x2. And so if you want to make this disjoint, you should remove the overlap from x2. But the overlap was all of x2 except for a single point, right? So as a set, x is just given by the union of x1 with a single point. And this is this is attempted to be illustrated here, at least kind of for the real points of this A1. So the real points are just the real line. So then you would have two copies of the real line. One, the outer one is x1, the inner one is x2. And then you start identifying points. You identify the point x with the point 1 over x on the other side. So for example, 1 is identified with 1, but then 2 in x1 is identified with 1 over 2 here. And similarly, 1 over 2 is identified with 2, and so on. And so almost all the points are matched up, except 0 on one side and 0 on the other side. They're not matched up. And so we see in the glued space, like we can, for almost all of it, we can just take x1, but then we have one extra point. And this extra point we want to call infinity. And the idea is, so it corresponds to 0 in x2. And the idea is, well, this 0 in x2 would correspond under this map here to 1 over 0, which should be kind of infinity in x1. Of course, this is not precise, but that's kind of the idea. In particular, you can imagine like a point going to 0 here. So it becomes smaller, smaller, smaller. Then it is true that 1 over this point would get larger and larger and larger in x1. So at least in spirit, it goes to infinity. But I mean, we don't have to rely on intuition. We can just kind of do the construction as we explained it. And so we get, as a set, x is equal to x1 union a single point. And the resulting space is called P1, the projective line. And we're going to see more about this P1 and then also higher projective spaces in the next chapters. For now, it's just the kind of first application of the gluing construction. If you want to not just do the real line, but actually the full complex plane, then you can do that. And then, I mean, it's harder to draw the picture, but it's still true that you try to identify z with 1 over z here. And then, for example, as z gets closer to 0 here, the 1 over z gets farther away from the origin. And then if you try to imagine what happens there is that, again, all the points away from the zeros get identified in some way from top to bottom. And the zeros stay distinct. And then if you glue them, in fact, you will get a sphere. So you can, for example, take the x1 here, and then the one point it added is this point here. And so you get a sphere, and this is called the Riemann sphere, CP1, which is C union infinity. So at least in the complex topology, we get something very nice, and we get something which is compact. The sphere is indeed compact. And that was one of the other complaints that we had about affine varieties, that it's hard to get a compact space. And before we conclude the example and go to another example, let's see a concrete map, because we can construct a map from P1 to itself now. And this is the way in which you can construct maps between these patched varieties, because we can say what the map should do on the individual patches. So on the patch x1, we say all of this patch x1 should actually go to the patch x2 on the other side by the identity, like this. And the same kind of symmetrically holds, we want to send x2 to the patch x1. And then what do you need to check for this to make sense? Well, we had a lemma which said that if you have kind of a set-theoretic map here, which agrees, or which on each patch of the cover here is given by a morphism of ring spaces, certainly the identity fits this, and which agrees on the overlap of these two spaces, then it gives a morphism of ring spaces. So somehow morphisms of ring spaces glue under open covers. So we do have to check that these maps agree on the overlaps. And well, if you start with something here, which is in the overlap, and then you first go on the other side, then you send z to 1 over z, and then take the identity here. This is the same thing as first taking the identity and then taking the map z goes to 1 over z here. So kind of this diagram here commutes. And so indeed we have the overlaps making sense, and we get a map from P1 to P1. This extends the map from x1 minus the origin to x1, which sends x to 1 over x, because that's what you get if you start with a point where this operation is well defined. And so if we see P1 as kind of A1 union infinity, then we get this map from P1 to P1, which sends, for example, 42 to 1 over 42, and it sends 0 to infinity, and it sends infinity to 0, because somehow 0 was the origin here, gets sent to the origin x2, which we call infinity, and symmetrically on the other way around. So we have constructed our first pre-variety, which turns out to not be an affine variety, and we have constructed the first map from this to itself. Very nice. There's a second way of patching the two affine lines, where the transition function is f of x equals to x. So this means 1 is identified with 1, 2 with 2, 3 with 3, and so on. And then, as I said, the kind of same argument as before tells you that the patch together thing x is x1 union a single point, the 0 from the x2. But now you see the picture is pretty different, because now this extra point looks like a second origin, because you started with two affine lines, and then away from the origin you always identify the corresponding points, but these are explicitly not identified. So they stay distinct, and so you get kind of an affine line with two 0 points. That's the semi-official name of this patch together thing x. And I just want to remark that x is a weird space in several possible interpretations. So first of all, if we go to the situation over the complex numbers, then you have kind of two planes like this, but now you really identify this point with this point, this point with this point, and so on, except for the origins. And then you get kind of a plane with two origins. And that's really not very nice space, because it is a non-Hausdorff space. For example, the sequence an equals 1 over n, this converges, and you can see it converges to both origins. Like you can always, whenever a small open neighborhood of the origins you take, you can always find sufficiently high n, you can find these points in there. So the sequence has a non-unique limit point, and so this shows this is not the Hausdorff space. So that's one way in which it's not nice. And then more on the algebraic geometry side, we can also write down a phenomenon which maybe we don't like so much, because we can do a very similar gluing as above. We can take x and then construct a morphism G from x to x, which, I mean, everything is, so somehow these two red arrows are just the same. We take the identity from x1 to x2, from x2 to x1. The same compatibility check. Now everything is an identity in this diagram. So everything is compatible. And so we get this morphism from x to x. And again, it has the property that it exchanges the two origins, because the origin x1 goes to the origin x2 and vice versa. But it is the identity away from the origins, because everything in the diagram is the identity map. And this property means that this set here, the set of x and x, such that g of x gives back x, well, away from the origin, this is always satisfied. But for the origins themselves, it's not satisfied. So this is given by a1 minus the origin inside x. We can take any of the two a1 minus the origins, either in x1, x2, doesn't matter. So it looks a priori a bit weird. Why do we consider this set here? But then you see somehow G is a morphism from x to x. And then the identity, which sends x to x, is also a morphism. And here we have looked at a set of the points where two morphisms coincide. And normally we would like to conclude if such a set is described by an equality of morphisms, we would maybe hope that this should be closed. I mean, certainly kind of the locus where two regular functions on an affine variety agree, that locus should be closed by what we have seen before. But here, this set is definitely not closed in there. For example, you can check this on one of these patches. So something weird is going on with this pre-variety X. And later, this example, among others, will motivate us to define varieties as pre-varieties plus extra conditions, which prevent such weird behavior.